Stafford from University of Brighton, and the title of his presentation is Robust Interpolation for Momentum Coupling of Dispersed Multiphase Flows in OpenFOAM using the Lagrangian Approach. Let me just say a couple of words about Chris. He works mainly modeling and simulation of particle-laden flows, developing an accurate continuum description of the particle phase using the full Lagrangian approach, and his mainly research interests are applied mathematics, computation of fluid dynamics, and particle-laden flow. Please.
Okay, thank you for the introduction there. Right, so the idea behind this talk really is applying a specific modeling approach for continuum and seeing how it can actually be implemented in software and how OpenFOAM comes into that. So I'll start off by introducing what the full Lagrangian approach is and why it might be useful, and then how we can actually use this for accumulating source terms. I'll touch on the implementation details and then show some results of the sort of things we can use this method to see in terms of details. So to begin then, the full Lagrangian approach. So just a bit of motivation. So this is applicable to the modeling of dispersed droplet flows, or indeed particles if it's monodisperse. And it could be applied in a number of industrial and environmental contexts. So the application of this work really is sprays, and in a general sense. And the reason we need this is the expense is obviously prohibitive due to the number of droplets in many scenarios in order to get statistical convergence. So what the full Lagrangian approach does is provide a description of this droplet phase as a continuum. However, this is only valid in a dilute suspension. So within the realm of sprays, we're looking post-secondary atomization, where we can actually truly model droplets as Lagrangian elements, rather than anything where we need to resolve surface stresses, and where that might contribute anything more than a negligible amount. So existing work has highlighted that 20 times fewer droplets in a simple flow can be used compared to a box counting approach, such as a cloud and cell method, which I'll be referencing later. And this gives you satisfactory accuracy. So in this work, we're going to be considering the potential of this to accumulate interface coupling source terms. So a bit of the detail then. So the central bit is the conservation of mass in Lagrangian form. And this is something we actually work out along a trajectory. And this is dependent on position as well as radius in this generalized format. So it's actually the conservation of probability we're considering here. But the key quantity is that we need to work out this Jacobian tensor. So for a polydispersed system, this Jacobian consists of this is block matrix. So it's got blocks in space, size. So R is radius. That's the metric of size we're using here for a droplet. And it's defined as a partial derivative with respect to the initial conditions. So if we want to consider this intuitively in terms of the spatial block, if we start off on a trajectory and we take a given element, say a square, what this Jacobian tells us is how that square deforms as we move along a trajectory. So physically, this is known as the Eulerian-Lagrangian transformation. It tells us directly the influence that a given droplet will have upon the Eulerian domain, which can be very useful. And so it tells us all about the deformation of the droplet phase spatially, and therefore the local structure of the Eulerian droplet field. So to illustrate this a bit further, this is just a demonstration in synthetic turbulence. This isn't OpenFOAM, it's just for illustration. But if we start a load of particles in a uniform array, and then we look at what happens based upon the evolution of the turbulent flow field, we see that we get defined clusters and voids. And that's just looking at the droplet positions and trajectories themselves. So for comparison, if we look at the full Lagrangian approach, we're now considering the element around each droplet. So starting from our squares, we can see how they deform, and they give us this same information, but in a much more continuous way that we're then able, and this means we can leverage that for the accumulation of source terms. So that's just an illustration. Another facet that comes into this method is that it's capable of capturing layers of the droplet field. So in particular, if we consider you might have inertial particles or droplets, two distinct trajectories could cross the same point in space with different velocities. Accounting for this in conventional or Arian solvers is a known challenge, whereas this method is able to account for it. So despite being multi-valued and having distinct layers, we can include that. A slight complication is that this Jacobian becomes 0 at these intersections, and our number density goes to infinity. So this has to be handled. So a quick appraisal of the method. It's efficient because we only need a seeding of droplets. We don't have to track many. We can track one parcel, and that's representative of many. We can account for different layers. It is only valid for dilute suspensions, and the number density can be singular. So, moving on to the source term accumulation. Because we only need the seeding, we can take a statistical approach to this. And for this, we're employing kernel regression. So it's glorified averaging using kernels to actually account for this spread of the droplet over not just the cell that a droplet's in, but neighboring cells. So this is just a statement of the Nadaraya-Watson estimator. The important thing is the selection of kernel. So we're using a structured kernel here, and a multivariate Gaussian is a simple form. But the key is we can specify this covariance matrix. And the important bit is that to construct the covariance matrix, we actually use this Jacobian tensor from the full Lagrangian approach. So that means that this domain of the kernel, which is this red disk for a spherical case, actually adaptively scales directly in accordance with the influence a droplet should have. So we've got an adaptive kernel, which is actually, this is essentially a form of statistical learning applied to the data that we have. So this is just in the case of droplets in space. We can extend this to polydispersed flows by increasing our phase space to include radius. It's relatively simple, case of just increasing our kernel to have an extra dimension. And then, in this case, our bandwidth matrix, we just use parts of the blocks of our Jacobian matrix to specify that accordingly. So that's straightforward, which is an advantage. And final bit of theory then is that because we're only tracking certain droplets, we need to know a size distribution or a distribution across sizes. So in this case, just using a log normal distribution as a representative sample. And then to actually accumulate the things or statistics of interest, we're looking at the average field variables. So what we're tracking and working out is this PDF, but by taking appropriate weighted moments of and integrating out the radius, we obtain number density and average size statistics, which are the things we'd like to know. So that's the full Lagrangian approach and how we're using it. So in terms of implementation, go through the equations first. So we're just using a standard transient flow solver here. So that's Navier-Stokes for momentum and incompressible flow. The droplet itself, we're considering to be governed by linear drag law, which is applicable in a dilute suspension. And the method could be extended in principle to account for added mass, etc. For evaporation, we're considering an idealistic model at this point where all the heat's spent on evaporation. And initial conditions, this comes onto the domain really, which I'll touch on in a second. And then the other half is this Jacobian tensor. So for polydispersed flows, it's a coupled set of ODEs, which we also solve along droplet trajectories and with associated initial conditions for each block. So the first two are second order because they're the motion. The second two are first order because they're just evaporation. So when it comes to actually putting this in a solver, I've made a custom full Lagrangian solver using the momentum parcel framework. So extending it to put the Jacobian equations in. And it's been coupled with PimpleFOAM as a general transient flow solver, although it could be used with any flow solver with minor modifications. So the evaporation and Jacobian have been implemented using the same time integration framework as the droplet velocity for consistency. And so the integration scheme is selectable at runtime in the input dictionary for the Lagrangian solver. And momentum is modeled using sphere drag, so it's representative of linear drag. We've implemented manual and patch injection for the case of steady state and transient scenarios. Initial positions at the moment generated using a script, just for flexibility. And then droplets are removed when they hit boundaries or fully evaporate. We can do this because they're just seeds. So it doesn't matter if we have one more or one less sort of thing. So the case I'll be considering is just a sort of fairly prototypical flow around a cylinder. So boundary conditions I've just put here for completeness. The top and bottom are periodic, and as long as these are far enough away from the cylinder, there's no effect on the flow. And then the others are fairly standard, fixed velocity at the inlet, and then zero pressure at the outlet. And the cylinder's got a no-slip condition. So that's the setup. So I'll go through some of the cases now for monodisperse and polydisperse droplet flows. So firstly, I'm considering two Reynolds numbers. So the lower one of 20 is a steady state case. In this configuration, we just inject droplets at the start and then track them. Reynolds number of 100 is transient flow. So we get a vortex streak forming and we have to inject droplets continuously. So start with the monodisperse case. So I'm just going straight to the results really. So the picture at the top left is what we get from applying this kernel regression to the full Lagrangian data. And we only need a subset of 121 droplets injected along the left. And we track them and we can form this picture. To do this using conventional box counting, to get convergence, I've had to do the same thing but with 12,000. Give or take, I've just done it with 100 times as many here. If you do it with many less, it's nowhere near as converged. And the difference is it's more well resolved along the wake if we used a higher number of droplets, but that's just because there's a slightly higher seeding near zero at the start. Away from this, the error is generally below 10 to the minus 1, which for a statistical representation is acceptable. And the disadvantage of the kernel regression is that it cannot capture high gradients as effectively, because the kernel smoothing length introduces it essentially means that having the steep gradients is that much harder. So in the case here, we can see that there's rapid variation in number density along the edges of the wake, and the kernel estimator loses accuracy in these regions. So moving on to a higher Stokes number now. So that was 0.1. So a Stokes number of 1, where we now have more inertial droplets. We can see that the higher seeding from box counting actually retrieves a bit more detail here, but this is only in areas of very low number density that aren't of much interest. And in general, we get an acceptable level of accuracy again. For the profiles, we see that actually the kernel regression captures the detail very well across the range of values, the y values, and the variation is more gradual, and that's why it's able to do this. So for a very inertial droplet flow, so Stokes number of 10, it's even more improved in a way. So the weight's still significant, and it goes to the edge of the domain, and we see that the accuracy is generally acceptable again, and in particular the profiles are captured well. So this is for a benchmark case of monodispersed steady state flow, and just comparing using cloud and cell accumulation as a reference. But the telling thing is that we can use 100 times fewer trajectories to get a very similar picture. So moving on to transient flow then. So in this case, we actually need to consider how it's evolving. And a reference here for box counting would be incredibly more expensive. So this is just a kernel regression, but we can, this is 101 seed droplets along the left edge, injected every 0.1 seconds. This is seconds to time. So we need several thousand droplets as this evolves, but we can use that information fairly effectively to get a picture of the droplet phase in terms of following the vortex streak. And we see that this kernel estimator is able to represent the rapid variation some statistical level at least at the edges of these vortices. So this is the low Stokes number again. For a intermediate Stokes number of 1, we see that the more inertial droplets, they leave much larger areas around the vortices. So we've got this area of high number density at the trailing edge of the vortices, and then behind them we've got some areas of very low number density. I point out here that the scaling, the colouring is logarithmic, so these big blue ovals that correspond to very low number densities, essentially that's just a cut-off between the blue and the white, which is negligible. So at a statistical level, this tells us quite a lot of detail about the flow, and importantly provides a smooth description in an Eulerian sense. So for the largest Stokes number then, it's a similar case again, even more inertial droplets. Striking thing in this case is that at the leading edge of each wake, we can see the folds or the different layers of the droplet field, where the different, I suppose, it's the trajectories going past each side of the cylinder, cross over each other. And the kernel regression and the full Lagrangian approach is able to capture this behavior correctly in terms of additive number density, which is something that's, like I said, difficult to achieve with Eulerian solvers for the droplet phase. So that's the monodispersed cases. Move on to the polydispersed ones now. So this is for the steady state case again. And what we're looking at here is a total number density over all droplet sizes. So I mentioned that we have to integrate out the sizes to get this distribution. And essentially it tells us that there's, as we knew from the, so this is an accumulation, if you like, of all the droplet sizes from the monodispersed cases. You can consider it in that sense. So we see that behind the cylinder there's the wake and an area of lower number density, and away from that it's fairly uniform. I've used 101 seed droplets along the left edge in these, and there's 41 different sizes in the range of Stokes numbers here. So this is just a number density. So next up, the next formula gave us the average radius. And so we can see that there's a higher proportion of larger droplets immediately going around the edges of the cylinder, but then in the immediate aftermath of the wake, there's only the very smallest droplets, is what this tells us. And then the next moment is the radius variance. And in general, the higher we go with these moments, the more sort of noise appears, which is just an inherent artifact of the statistical procedure, but it's qualitatively the same as the size, average size. So that's the steady state cases, and I'll go briefly on to the polydispersed cases. So before I do, so I mentioned I integrated out the size distribution. Actually, you can visualize slices of this, so we've got a full, these are 2D example simulations, but the data set is actually 3D because we've got this extra dimension in size. So the information we can get from this procedure is we know the size distribution of droplets at every point in the flow field. And these are cross-sections at various distances behind the cylinder, showing the distribution in sizes. So it's symmetric, as we'd expect. These are the Y values. So that's just to illustrate the level of information we get from this procedure. So final one then is the polydispersed cases for this, also the transient case for the polydispersed flow. So this is the number density, and we're looking at all droplet sizes here. And in general, because they're inertial droplets, they're all ejected from the vortices by virtue of that, but we see there's a spread of locations in these areas of higher number density, depending upon what inertial droplet has. So this required more droplets to actually construct the picture. So as well as our different sizes and number of seeds, we're injecting them regularly again, just so we can get the full transient picture. And as with these monodispersed cases, we get clustering occurring along distinct curves. So for the average droplet size then, it's a similar picture. we've got some behavior at the leading edge here where the initial behavior is, but then we see that it's generally in and around the vortices along these distinct curves where we get larger droplets, while in the vortices it's only the very smallest ones really. And then we get larger droplets on average going around the cylinder again. And then, just for completeness, the variance in droplet size. So the range of droplet sizes at a given point is high because we've got most droplet sizes going past the cylinder, but then quite low in the vortices themselves. So that's a summary of the sort of information we can get from this method. And just the final bit then is I suppose the full data set, or slices of it at least, for the transient flow. So in this case, the flow is non-symmetric. And we can see that in some places we don't have the largest droplets, and that this region moves depending on how far behind the cylinder we go. And the strength of the method is that we're able to obtain this information and as a fairly complete picture. So, quick conclusion then. So, ongoing work, the real application of this is for momentum coupling, and that's something which is still being done. So, actually putting these number density and average size or velocity distributions you can obtain similarly into OpenFOAM in terms of interface coupling, and then updating the source terms for arbitrary meshes on the relevant cells. So at the moment, just working out an efficient cell lookup to actually minimize the cost of implementation, because you want to keep it as minimal as possible, really. And then actually extending it to polydispersed flows, it requires integrating out the sizes. So that's again ongoing. So conclusion then. So the basics of the transient generalized fully Lagrangian approach has been implemented within OpenFOAM. And we've seen that kernel regression accumulates these contributions based upon the structure of the concentration field for the droplets in a smooth way. And we can use this for coupling source terms. It's straightforward to extend for polydispersed droplets, and we can generate a complete picture of the droplet size distribution at any point in space. The statistics can be obtained directly, so we've got number density, average size, etc. And the reference, we've seen that we can use of the order of 100 times fewer droplets, I should say, than the cloud and cell approach to get a statistically converged result. So just quick acknowledgement then, funding it's a Future Leaders Fellowship for my manager, and to thank the High Performance Computing Cluster too at the University of Brighton. Okay, thank you for listening. I'm happy to answer any questions.
Okay, thank you, Chris. Thank you very much for your interesting presentation. Questions from the audience, please?
Yeah, so what I understand is you use a stencil to determine the source attributes to the continuous phase.
Yes.
And there's also a shape involved of this stencil. You say involved with the code.
Yes, so the kernel, actually, the structure of it. Yes, so that's one of the facets of the method. I mentioned the area of this shape collapses to zero when you get crossing trajectories. So you have to set an artificial limit to how long and thin it can get. So, for instance, if you were doing this in turbulence, you wouldn't want a contribution to be longer than an eddy size, say, because you'd get unphysical results. So yes, well picked up. Sorry, my ensemble.
Well, you say when you determine the drag on the particle, but now you also know that you've got a set of particles in a certain.
So no, I mean the particles we use them as parcels, but we just model them as individual particles. So the drag coefficient is just a standard linear drag in this case that doesn't depend on that shape or anything. the particles are modeled just as spherical.
But the effect they have on the previous phase is if they have a distant ensemble with a certain shape. And if I would use the particle cell method, and if they be all in each other's wake, then they have some effect on the
Yes, there would be, yeah. So that's one of the limitations of the method. It's only really applicable to dilute suspension, so below the level of four-way coupling, where you're considering wakes and collisions. So once you get to that level, this wouldn't be applicable. So that is a limitation.
Any other question? Okay, if not, let's thank the speaker again. Now we have next presentation is from Mahidul Haque Prodhan. He is a PhD student at University of Leeds, and his presentation title is Large Eddy Simulation of Particle Deposition in Pipeflow using OpenFOAM. So, please start.
A very good afternoon to my presentation. I am Mahidul Haque Prodhan, a PhD student. I am a new beginner of OpenFOAM. I am just finished my first year. And this is my first presentation, international presentation in first international conference. Hope so I will present. So my topic is large eddy simulation of particle deposition in Pipeflow using OpenFOAM. Basically, I have not completed any final results. I am sharing some part of my PhD study that I finished, and that is basically in validation phases. So my research focus, basically, particle separation from flocculate waste, especially concerning nuclear waste, using CFD method. The main objective of this study is to predict complex particle sedimentation and deposition in transport pipelines using large eddy simulation in OpenFOAM, coupled to discrete Lagrangian particle tracking. The outcomes would be direct significance to the behavior of two-phase flows encountered during nuclear waste processing and transport, and have consequences for particle dispersion, agglomeration, and deposition in pipe flows transporting such nuclear waste, and then extended it for a large channels. Here, models of particle aggregation and breakup will be coupled with semi-empirical fractal sedimentation models to give realistic separation physics without high concentration time costs. In future, this study will also attempt to provide high-quality experimental data for validation purposes, where flocculated aggregate size and concentration parameters will be measured in situ. This is the picture of Sellafield nuclear waste pond. There is so much scopes to do work regarding clarifier and hydraulic transport lines. Basically, these are one of the most common unit patterns for primary separation of flocculated waste. Performance issues like the formation of strong inlet circulation, currents that can increase the presence of solids in outlet flow are key factor in design. So as a result, consideration of industrial unit is significant, where CFD is often used to simulate this stuff. However, CFD methods do not adequately like the physics of complex and shear dependent flocculated particle phases to the field and the fluid condition. Hence, to better identify, my main primary goal that I told already is that the predict of complex particle sedimentation and deposition in transport pipelines initially using large eddy simulation coupled to discrete Lagrangian particle simulation, and then adopting a realistic modeling approach and analyze the characteristics of complex flocculated waste sludge suspension separator, especially nuclear sludge waste. In this presentation, only single phase pipe flow and multi-phase pipe flow validation was completed by comparing fluid dynamics to direct numerical models. It is to be noted that DNS data collected from a paper, Bremen 2007, and DNS data also validated by the Bremen with some experimental data. In future, my goal is Lagrangian versus Eulerian methods for solid fluid flow simulation through 5 or channel and prediction of critical deposition velocity versus analytical models for Lagrangian versus Eulerian methods. And then validation of Eulerian population flow models and extended to use sedimentation model for channel settling tank. Then to model the aggregation and breakup of particles, computationally efficient, and therefore incorporate that into sedimentation and flow modeling in case of clarifier. So here methodology is fluid phase modeling, alias turbulence model, and multidimensional modeling and Lagrangian particle tracking. Here I used OpenFOAM CFD software, and in some cases of extracting data and plot the graph, I used also Paraview and Python and Origin Pro also. So here are some questions. Why alias is preferred here over other choices? Why Lagrangian particle tracking? And why particle simulations in OpenFOAM? In case of alias, results are more accurate than RANs, less computational cost than DNS, and solve small eddies with a subgrid scale model. Good alias resolves at least 80% of kinetic energy, and the remaining is modeled in subgrid model. We know that in case of alias turbulence model, large eddies are completely resolved as well as small eddies are completely resolved by SGS model. And RANs is also used while bulk quantities are looked for, although if evidence recommended that RANs models are incapable of demonstrating crucial turbulent quantities regarding unsteady cases. So alias be able to solve better smaller scale message grid than RANs. Furthermore, in case of unsteady simulations, alias bounces dynamic turbulence that can perform to understand particle and fluid flow patterns, concluded complex geometries. So basically I chose here alias model. Why Lagrangian particle tracking? Basically fluid flow often carries solid particles with them. We can track very light particles using streamlines, but heavy particles should fall down. Particles should also move slower than the fluid due to drag force, and we can not use streamlines for these particles. And so I chose the Lagrangian particle tracking. So basically, this is the headline is why we use the OpenFOAM in the particle simulation. Basically, OpenFOAM is free open source, and OpenFOAM is constantly under development with a continuous growing community, academic research, R&D in companies, and OpenFOAM includes the solver for any application of particle laden flows, processes engineering, mechanical engineering, civil engineering, physics, and also others. And already different solvers for any kind of particle laden flows are already implemented in the OpenFOAM. So here I just accumulate the difference between dilate flow and dense flow. I know you already know it. Basically, dilate flow particle motion is controlled by the fluid forces, that is drag and drift, and dense flow particle is motion controlled by the collisions and continuous contact. And here is the coupling mechanisms, that is one-way coupling, two-way coupling, and four-way coupling. I am completed the one-way coupling, and now my simulation is running for the four-way coupling. So this is my mesh and different components of this here. And this is my some results of validation. So here is the stream-wise. I basically used as a fluid the air. So air stream-wise mean velocity versus radius. So here is the basically mean velocity and RMS velocity. This is the RMS air stream-wise RMS velocity, and this is the radial RMS velocity, and this is the renal shear stress, and this is the basically y plus u plus vs y plus, and all RMS velocities are here. So here is that these are the fairly good agreement with the DNS data of the Bremen 2007. I expect with the longer run of the my simulation, I hope this agreement will also be better from now. So I also use same mesh for the multiphase simulations. Here I try to use the 29,000 particles and my particle diameter is 60 micrometer. Here is also I get some results, that is mean velocity, RMS velocities, and radial RMS velocities, and all RMS velocities are here. And I accumulate the all RMS velocity and shear stress in a graph. And here also I can see that from the comparison of DNS data of Bremen 2007, a fairly good agreement of the DNS results. However, I also again say that more averaging from the longer run, it will be a good agreement, a better agreement from now. So in this presentation, Elias carried out the fully developed turbulent pipe flow, both single phase and multiphase was validated. The code performance has shown fairly a good alignment with the experimental result in previous different research studies. However, I always say that more averaging for a longer time needed. Current work is also looking at four-way coupling that I already told to comprehensively track the influence of the particles on the fluid properties. So now my particle deposition simulation already also running. I am also working regarding to verify my models with Haque's, this is a paper, critical deposition velocity model. Also fully working for now a clarified design and a flocculation system phenomena, and hopefully I will be able to complete my literature review and will be able to make a design very soon. In case of flocculation, I am trying to use population balance model regarding aggregation and breakup, which is now fully studied. So I am trying to accumulate this algorithm, the combination of Euler-Lagrange method with PV in OpenFOAM that I am now trying to study and trying to implement in the OpenFOAM. And in the OpenFOAM, these are two loops, Eulerian and Lagrangian loop. And basically, I am trying to simulate within the next 3 years. I hope in the next conference, I will show you some good results. Thank you so much.
Thank you for your presentation. Any question from the audience? That was very fast as a presentation. Can you go back to the validation you have performed to this side? You were speaking about the need to improve the agreement between copied and experimental data. Why?
In case of longer runs, if more averaging, I think my Elias results with also good agreement with the DNS data.
Because I think that already the agreement looks
yeah, already
quite,
but near I think it is better near for a longer run.
Okay. More questions? Okay, so let's thank the speaker again. Okay. So now we have online presentation from Rahul Subburaj from Technical University of Eindhoven. Rahul, are you online?
Yes, I am here. Yeah.
Hello. Hello.
Hello, everyone. I'm Rahul. I'm working in TUE under Niels, and I'm going to talk about an improved lift model in Euler-Lagrange simulations. Before we move to the Euler-Lagrange simulations, let's talk about bubble column reactors. So basically, bubble columns are just a bunch of bubbles in a column. Simple. and they have a high mass transfer and heat transfer, and it's used for chemical applications. And usually it's the transfer is from the gaseous phase to the liquid phase, and the reactions happen inside the liquid phase. And in our work right now, we focus on the hydrodynamics. And for simulating the hydrodynamics, we use Euler-Lagrangian framework because it's not too dense. So we should be able to use it. And for tracking the free surface, we use the VOF model, VOF method. And before we move to the equations, how it's solved, let's talk about how the volumes are treated, because we have two volumes here. One is the discrete phase, another one is the continuous phase. And we can, just a moment. Yeah. And we can see that if we take the total volume of the cell, it can be divided into two, the discrete phase, which is the bubble, and also the continuous phase, in which we have liquid and gas. So we can have, if we multiply alpha C multiplied by alpha L, we can get the volume of liquid in the continuous phase, and vice versa for alpha G. And we should be able to get equalities like alpha L plus alpha G equals 1 and alpha C plus alpha D equals 1. This is just taken from the paper given below. And using this, we have some implementation, which we do it in OpenFOAM. What I do is I just use the modified GPM foam to solve the particles. And I use the interfoam to solve the free surface. And of course, the rho is just the continuous phase density. And we are going to focus on the forces, one of the forces, lift. So we focus at this. I'm not going to focus on other things because, yeah, we have to save time here. And why am I focusing on lift? Because it's one of the important forces. And what is lift? Basically, it's the response to shear inside a flow. And you always have some kind of strain or shear. And it's usually responsible for a bubble spreading. And the bubble spreading, in turn, it determines what's going to be the stability of the plume. And yeah, so some papers observed that depending on the size of the bubble, we can have different lift. That is, for smaller bubbles, we can have positive, and for bigger, negative. That means smaller one will move towards the lower velocity side, and the bigger one will move toward the higher. And this is expressed, the forces are expressed in terms of an expression, which is multiplied by a CL, which is a coefficient, lift coefficient, and the vorticity and the slip velocity. So all of this contribute to lift. So what models do we have for lift? So most commonly used lift model is Tomiyama's model, where it's just the same observation as before. That is, it's positive lift for smaller bubbles, and it turns negative for higher bubbles. So you have to ask this question: is this lift model enough? Because there's a problem. This lift model was observed only for single bubbles, and we are going to use a lot of them. So what do? We test it. We test our lift models. And we have a column setup, which is from Dean's case of 2 column heights, liquid heights. It's 0.45 meter and 0.9 meter. And the column width is around 0.15 meter. And the grid size is 5 millimeter, and the bubble diameter is 4 millimeter. And the injection rate, all of the details are given here. And the solver name, I've called it the DPM colliding foam. And these are the different models I use. The first one is the drag, gravity, pressure, and virtual mass force. These are no-brainers. And we test these 2 column heights with 2 different lift coefficients. One is 0.5 and 0.3. 0.5 is it's called the constant lift model, and 0.3 is just, it comes from the Tomiyama's model. So how would it look like for the shorter column height? Yeah. For the shorter column height, we can see that CL equals 0.5 is much more closer to the experiments. compared to CL equals 0.3. Already we are seeing that Tomiyama model doesn't work in this case. And of course, higher CL means higher spreading, which is obvious, and this as well. And when we change it to the taller column, that is a 0.9 meter, we see that CL equals 0.3 is better than CL equals 0.5. The case with the simulations with CL equals 0.3, and this is what we expect. And then we already see that we are using different CLs for different aspect ratios, which is not really nice. And this is how the bubble plumes look like for different CLs, lift coefficients, and for different heights. So you can expect that for higher CL, there is higher spreading, and the same thing. And what we do is we try to observe more. What are we seeing with this different CL? And at a higher region of the column, we observe that both lift models don't work properly, and this is just it is observed in our case. And also the amount of spreading we have seems to change with height as well. And then the problem is now that we don't really have a universal CL. So how do we fix this? We must have some sort of a strategy for this. So what I will implement is to find a lift coefficient that changes with height. That's what we observe, that CL is changing with height. And we just take an initial guess and find out which one works the best. And it is correlated. This CL versus height is just a temporary relation, and then it's correlated to different governing variables for a better fit. And when after a lot of trials, I found that these two lift profiles are working better for the two cases. That is, for the shorter one, we have changing from 0.6 to maybe 0.3, and the taller one we have changing from 0.6 to and 0.6 to 0. That is, at 0.35 it's going to 0, and this is what we observe in taller columns as well. That after a certain height, the spreading stops, and that's what we're observing in this CL graph. And these are the results. I have to show you to make it believable, right? At 0.15 meter, we see that it's very close to the experiments, and at 0.35 there is a slight underprediction, but this is kind of seen in all lift models. And at for the taller ones, we see that it's also close to experiments. You can see it qualitatively, and this is the best part of the presentation, where we don't see any backflow like we saw in the previous case. There's a proper central upflow. That's good. So we are on the right track here. So we found really good two lift distributions. Now we just transfer it to different governing variables. So what variables do we pick? So we have to look around, and I found a paper by basically a thesis by Subburaj stating that gas fraction and local turbulence, they determine CL. And also there was another paper which said that vorticity also plays a role in this. And what I do is I have the information with height. I have to get data points from my simulation. So what I do is I try to average the bubble properties. I first separate the bubble column into several subsections, and inside the subsection, I find the averaged properties so that I can get what's the alpha G there, or wobble number there, and try to fit it with CL. And this is the expression. This is the expression for the averaging that's happening inside. And what we get out of this is a relation between CL and different variables like gas fraction, vorticity, and wobble number. You can already see that most of these are increasing relations. So what we do is, in the end, find a fit. Which one does it work? Which relation does it work? So we have 4 models which we test whether it works or not. The first one is just with alpha D, which is the which is the discrete phase gas fraction, which is basically the bubble gas fraction. And the 2, 3, and 4 are a combination of wobble number and vorticity. And it's the same settings as stated before. The only thing that's changing is CL. And we see that equations 3 and 4, they're really close to the experiments at both heights 0.15 and 0.35 for shorter column. And the same thing, and these are just the RMS results. And the same thing for the taller column, where we see very close. There is some slight deviance, but compared to 1 and 2, it's better. And equation 3 and 4, again, they perform really well. And the statistics also, yes. There is a slight underprediction for equation 4, but it's all right. That's something to do with the turbulence model. So we can conclude equations 3 and 4 work better. Now, there's a problem. We have a dilemma. Is it 3 or 4? So we use another case, and this case is by Hartefeld. And these are the case conditions. And the column height is 1. It's a rectangular case, which looks something like this. And there are 95 injectors with 6,000 bubbles per second, and the same bubble diameter, which is really important. And the grid resolution is 5 millimeter, and these are the force models, the same thing as done before, and we test the 3 and 4. And then we see at a height of 0.05 meter, both of them are very close to each other, but at a height of 0.2, equation 4 is very close to the experiments by this small wall picking, which maybe can be done using wall force, which I have not included in my analysis, which can be solved. But the equation 3, it's deviating a lot. And then this can be seen at higher heights, where the deviation is even more. So we can conclude that equation 4, and this is another one, where we compare gas fraction data. And then we see again that the red line is way close to the experimental results, which is the blue dashed. So we can conclude that a CL, which is a function of alpha D and omega, it works the best, but there is a limitation. We only have a data for bubble diameter with 4 millimeter, and yeah. So we conclude that the lift force it's non-linearly dependent on vorticity. So we have a relation, but does it make sense? I don't know. This is something I have not figured out yet, but I tried to find some trends which could tell you why it depends on omega and alpha G, which is the gas fraction. That is a bubble fraction. I found a relation, which is a CL versus omega, which is the omega max, which is the maximum vorticity, and a function of the terms are the deformability in blue. That's just the deformability of the bubble. So I was thinking that maybe if the bubble is very close to each other, the deformability will change. So in our bubble diameter, that is 4 millimeter, the deformation is controlled, it's modulated. So it's possible CL increases. And for larger bubbles, it might be a completely different trend. So I don't know. Maybe future experiments and DNA studies will help us understand more. And these are the references for anyone. I'd like to thank MSEC for funding my project, and my supervisors, Niels and Yali. And finally, thanks to the OpenFOAM team, because without them, there would be no variable lift. And any other questions? You have questions?
Thank you very much, Rahul, for your interesting presentation. Any question from the audience? No questions. Let me check online. But don't worry, because I have a question for you. So I will just let me just check in the chat. Oh, there is no. Okay. Rahul, can you go back to the slides showing the model, and can you maybe clarify the reasons why you have to solve one, let's say, multiphase equation like interFOAM, and then use also the Lagrangian particles?
Oh, yeah, this one, right?
Yes, yes, exactly.
It's a really good question because I didn't tell you why I'm using it. There were simulations which were using only the Lagrangian solver, but the problem is when the Lagrangian solver moves out of the domain, that is, the particles move out of the domain, the fluid is also dragged along with it. And to avoid that, what we have is we keep a free surface. That is mass conservation inside the system. Does that answer your question?
Okay. Okay, it's clear.
Yeah.
Other questions? Okay, so if there are no other questions, let's thank Rahul again for his presentation. And we can move to the next, which is also the last presentation of the session, from Yong and Huangwei Zhang from University of Singapore. Are you online? Okay.
My presentation is transmission of a hydrogen detonation wave across a dilute particle curtain. So this presentation outlines include about 6 sections. So firstly, I will introduce my research background. As you all know, hydrogen as a clean fuel, it can help reduce carbon emissions. However, hydrogen leakage can cause ignition and detonation due to its lower ignition energy and whether detonation limited. The blue figure shows some hydrogen explosion accidents in South Africa, US, and Japan. So to mitigate a hydrogen explosion or detonation, here we choose particle curtain. This photo shows the particle curtain between the 2 dust lines. So we use particle curtain because it is easier to obtain, cheap, and safe to use without additional damage. Their mitigation mechanisms are that it can reduce the overpressure, propagating speed, and product gas temperature of the detonation or blast wave. So here, this figure shows some key literatures on shock or detonation inhibition by particle curtain. So we conclude that they consider particle curtain properties such as various particle size, particle concentration, and curtain length. And various curtain property result in different propagation modes of detonation wave, such as detonation transmission, detonation extinction, reinitiation, and pulsating detonation. Moreover, they also observed the detonation velocity is reduced with decreased size, increased particle concentration, and the curtain length. These authors merely attribute detonation mitigation mechanisms to interface exchange of heat and momentum. Although there are a lot of work on the detonation inhibition by particle curtain, there are still some key points that are not well understood, such as the first point is detonation regime map predict from parametric study, and details of unsteady dynamics of detonation subject of particle curtain. And the third point is chemical explosive mode analysis of detonation extinction and reinitiation. So here in this presentation, my research objective include validation of numerical method on the shower, identification of detonation and propagation extinction in gas particle two-phase mixture, unsteady dynamics of shock subject to particle curtain, quantification of chemical reaction information with chemical explosive mode analysis. Our research method is hybrid Euler and Lagrangian approach with two-way coupling. So the Young equation for gas phase include mass, momentum, energy, and species conservation equations. And for the particle phase, here the Lagrangian method is used to check the dispersed particle phase composed of a larger number of spherical particles. The parcel is used in our simulations. Parcel is an ensemble of particles with identical properties such as the same particle size, temperature, velocity, and density. As shown in this figure, there are many particles in a partial. The Young equation of momentum and energy for the individual partial, such as the particle velocity, is determined by drag force and the pressure gradient force, and the particle temperature is controlled by convective heat transfer rate. So the gas phase and the particle phase equations are solved with our Rosen form, which is developed from the standard solver Rosen form in OpenFOAM. Our group solver Rosen form can resolve multiphase, multi-species, complex, and reacting fluids. This figure shows the key structure of the solver Rosen form. It has two sub-solvers, Lagrangian solver for gas phase and Lagrangian solver for dispersed phase. The Lagrangian solver has three key blocks: multi-species transport, chemical reaction, shock capturing. The Lagrangian solver in this simulation has two blocks: particle force, heat transfer, and they interacting with each other by exchanging mass, momentum, and energy. This table shows the computational method. Second order backward method is used to discretize unstandard term, and the muscle type region solver frame scheme with value limiter is implied for convective flux in the momentum equations. Total variation diminishing scheme is used for convection terms of energy and species equations. Second order central differencing scheme is used for diffusion terms. As for the Lagrangian phase, their equations are solved by first order implicit Euler method, and the gas property at the particle location are calculated based on linear interpolation. So blue are some validation work. The first case is multi-component insert stock tube. It aims to validate the convection scheme and thermodynamics property calculation. And the second case is perfectly sterile reactor. It can be used to examine the accuracy of the various integration methods for chemical reaction short term and the calculation method for chemical kinetics. The third benchmark is two-dimensional cylinder explosion case. It is conducted to validate this solver on the two-dimensional Euler equations. The final case is two-dimensional detonation in premixed hydrogen air mixture. It is started to examine the capacity and accuracy of the Rosen form to predict the cellular detonation from structure. So in this computation domain, we use the third block to record the peak pressure trajectory of detonation wave. So the figure has two equivalence ratios. So we compare the simulation results with experimental data and theoretical calculation as indicated by the red box. So the conclusion is the accuracy of the Rosen form in calculations of detonation cell size are generally satisfactory. So the blue is our research work. So it is a two-dimensional domain with 0.3 meters long and 0.025 meters width. It has two sections, device section and two-phase section. The detonation is ignited with 3 hotspots in the left end with high pressure and temperature. And finally, it will generate a planar detonation wave before approaching the two-phase section. For the whole domain, it is filled with stoichiometric hydrogen air mixture with initial temperature 300 Kelvin and initial temperature 0.5 atmosphere. So the detailed chemical mechanism is from Berg. And for the particle phase, it is uniformly distributed in two-phase section. The curtain length is no longer than 0.1 meters. Here we set that each cell has a single particle, and the particle number in a single particle can determine the particle concentration. Curtain length is no longer than 0.1 meter, and particle size from 2.5 to 10 micrometers, and the particle concentration is no more than 2.5 kilogram per cubic meter. So here is our summary of the research results. So it is the curtain length as a function of particle concentration and particle size. The solid line is critical curtain length, and the open symbol means that the detonation extinction, and the solid symbol means stable propagation of detonation wave. So from the detonation regime map, we can see that critical curtain length decreases with the particle concentration. This is due to higher particle concentration corresponds to larger transfer of momentum and energy. Moreover, with increased particle size, the concentration range to have detonation extinction is appreciably elevated when the curtain length is fixed. This is because smaller particles with larger specific heat exchange surface area are more likely to weaken the detonation wave through stronger heat and momentum absorption. So we select one case. I think we believe the most important case to illustrate the two-phase detonation structure. The left figure shows the gas temperature, heat release rate, particle temperature, and their energy transfer, gas velocity, particle velocity, and their momentum transfer. So let's look at the inductor wave. This shows some basic detonation front structure, such as shock front, include incident wave and match steam, reaction front, transverse waves, triple point, and jet flow. And the right figure are the weighted average the results of left figure. So in figure 8, we found that the heat release rate increased behind the shock front and peak at reaction front. And the shock frame Mach number is significantly decreased behind the shock front. Figure B shows the temperature field. We found that the gas temperature is significantly increased behind the shock front. However, slightly increased phenomena is observed for the particle temperature. Their energy transfer is also significantly decreased behind the increased behind the shock front. In figure C is the velocity fields. Different from temperature evolution, we found that the gas temperature peak inside the induction zone between the reaction front and the shock front. And the particle velocity is still slightly increased. And their momentum transfer also peak inside the induction zone. So the last figure shows some key radicals change with the x direction. ER is local equilibrium ratios, and so we move on to the next figure. This figure is a time history of temperature field. It means the detonation, extinction, and the reignition process. For the first instant, the detonation wave is still stable propagation. After some time, we found that most of the stable detonation wave are decoupled, but some localized detonation combustion phenomena along the shock front are still observed, such as at 120 and 124. And a reignition point appears near the upper boundary. And this reignition point will evolve into a overdriven detonation wave. Finally, for the last hand, it becomes a stable propagation of detonation wave. So the next figure will explain how the reignition point generates. So the left figure is an eigenvalue of chemical explosive mode, and the right figure is pressure gradient for magnitude around the reignition point. So let's the five larger waves are from the red box in figure D. So figure A is in this figure A shows the eigenvalue of chemical explosion mode indicates the chemical explosive propensity, such as we can see that a larger value occurs behind the shock wave 1 and the shock wave 3. It means higher explosive mixture occurs behind the two shock waves, and the lower explosive gas mixture appears behind the shock wave 2. And if we see the both two figures, we find that the two propagating transverse wave are approaching each other from 123.5 microsecond to 123.8 microsecond. And in 124 microsecond, the two transverse wave shock focusing leads to the formation of a reignition point with high pressure and larger value of eigenvalue of chemical explosive mode. And the last two figure, we can see that a new match stream is developed from this reignition point, demonstrated with coupled reaction front and shock front. And it is also evidenced by the larger value of chemical explosive mode before the reaction front. So here we discuss the particle current phase. The figure shows the velocity fields of the particle current. Here the up front and down front of particle current are determined from wide average volume fraction when it is greater than 1% of initial value. So from 110 to 118 microsecond, we find the shrinking regime. It is induced by velocity differences of two fronts, such as when upper front velocity is larger than the down front velocity, and the particle velocity are usually markedly reduced along the propagation direction due to shock acceleration, and from 140 to 180 microsecond, constant velocity regime is found. Their relative velocity and distance are generally unaffected. For the last three time instants from 220 microseconds to 340 microseconds. We found an expansion regime. It is featured by the increased thickness due to the pronounced velocity difference between the lower upper front and higher down front. So we use, this figure is a displacement of up front and down front on particle curtain. It is colored with average the volume fraction of inert particle. So we can clearly see that the evolution regime has three stages: shrinking regimes, constant velocity regime, and expansion regime. So the above the research work are introduced, and we can draw some key conclusions. So in this talk, the fluid geometric hydrogen air detonation propagation in inert particle curtain with finite lengths are simulated by Euler-Lagrange and Lagrangian method with gas particle two-way coupling and detailed chemical mechanisms. The solver average center form is implemented in OpenFOAM, and the numerical methods are compared against with theoretical data. But the results shows that the average center form has satisfactory accuracy. A detonation propagation map is predicted from parametric study. Two-phase detonation frontal structure and the Lagrangian particle curtain evolution are well captured by this solver. Detonation reinitiation is analysis with chemical explosive mode and pressure gradient magnitude. For the future work, we consider the dense particles different from the dilute particle. In the action of the shock of detonation with the dense particles will exhibit new features such as the clonomorphic evolutions, average volume fraction, velocity, and interface exchange. So thank you. That's all.
You for your very nice, interesting presentation, and we are sorry for all the technical problem you have encountered. Questions from the audience? No questions. Let me check in the chat. Unfortunately, no questions in the chat. So I have one. Can you go back to the slide where you described the model? I think no, it was probably before, very at the beginning. No.
You mean the Gaussian equation or the?
You were showing a slide where you no, the test case. Sorry, the test case that you have presented. So no, go down. Go down again. So, no, it was probably the real. Yes, next one. Next slide. Sorry. Okay. Yes, exactly. So the particles are treated with the discrete element method or just Lagrangian approach?
Oh, okay. Thank you for your question, Professor. It is point jobless. We use the PSI cell method.
Okay.
It is not resolved by the solver.
Okay. Thank you. Thanks for that.
Thank you.
More questions? Okay. If there are no questions, let's thank the speaker again, and let's also close the session. I would like to thank also the people that are managing all the connection and the audio and video that really helped a lot during this session with the management of all of the issues we had. Okay, thank you also for coming.